Now, as a homework, this is very important that you do this. Consider the poset over the positive integers n plus, ordered by the divisibility relation. Now we looked at a small subset of this earlier. Now prove that its Mobius function is given by mu of r comma s is equal to -1 whole raised to t if if the number s by r is a product of t distinct primes. Okay, so if s by r is a product of t distinct primes, then mu of r comma is equal to -1 whole raised to t, which is the number of distinct prime factors, distinct primes of s by r. So t must be precisely the product of t distinct primes. It cannot have a prime square, for example. So in other cases, like all other cases, it is going to be 0. So if s by r is containing a prime power, for example, then this will be 0. But otherwise, it is going to be -1 raised to t, where we have exactly t distinct primes. Now, so this is your homework. Now we look at what we wanted to look in this section, which is the Mobius inversion. So let P be a poset with a 0. So if you remember 0, we defined in the previous lecture, right? So so this is actually a simplified statement. In fact, one can make it a little more general. So what we really need is that the poset should have all its primary principal order ideals to be finite. So what is the principal order ideal? Okay, I'm not going to write the definition, but to be brief, so if you take an element, right, all its all elements which is less than or equal to this must be also in the ideal. Okay, so that's an order ideal, and so a principal order ideal is the order ideal generated by a single element. So all its principal order ideals are finite. Then then we can do the same proof. It will work. So the main idea is that when you telescope the sum, it should stop at some, and if you are considering finite posets, it's basically equivalent to the same statement, because you can always add a 0, right, and then make it equivalent to this. But for our purpose, this is good enough. So now let f and g be functions from real valued functions on P. Then g of x is equal to summation y less than or equal to x f of y for every x in P, if and only if f of x is equal to summation y less than or equal to x g of y into mu of y comma x for every x in P. So where mu is the Mobius function of the poset P. So this is called Mobius inversion. Okay, so it says that this the f and g are functions from P to R, or in fact P to C also works well, if and only if if whenever g is expressed as a sum of f this way, right, f is expressed as a sum in this way. So this result is called Mobius inversion, right, and this is quite easy to prove. So what we do is we just use the definition of the convolution product, and then just work out the detail. Okay, so just look at this. So the summation y less than or equal to x g of y into mu of y comma x. So what is that? This is, so that is what is given here, right? So So we want to show that this is actually f of x, right? So g is given this way. We are going to show that this is precisely what is. So we will start with on the right hand side and then work it out, right? So this is basically what is that summation. So this is by the definition of the product, right? So g times mu is defined as summation over y less than or equal to x, summation z less than or equal to y, f of z into mu of yx, because I can write g of x in this way. Now, this is basically summation y less than or equal to x, mu of y comma x. Summation overall z belong to be zeta of zy into f of z. So this is where the magic happens. So we use the zeta function here because zeta function, as we observed before, is one precisely when z is in the interval that we want. Otherwise, it is going to be 0. So therefore, I can just add zeta here to do this. Now I can do a reordering of the summation, right? So changing the order of the summation, this I can write as summation z belonging to p, summation y less than or equal to x zeta of zy into mu of y comma x f of z. But now this one is in as a convolution product, right? And zeta and mu are inverses of each other. So therefore, this becomes delta. Right? So therefore, this is basically delta of z comma x. And so we get summation z belonging to p delta of z comma x into f of z. But delta function is precisely 1 when z is equal to x, and otherwise it is 0. So therefore, the only one term it survives is when z is actually equal to x. So therefore, this is actually equal to f of x. And that is precisely what we wanted to prove, right? So since all these steps are reversible, we yeah, so we get this identity. So how to use the Mobius inversion, right? So here is some example. So consider the example that we looked at, the natural numbers with the usual order, which is a chain. Okay. Now, in the previous example that we looked at for computing the Mobius function, we only looked at a small subset of n, right, 1 to n. But one can see that because of the telescoping property that we observed, it works for all the n. So therefore, the Mobius function of this poset is also given by mu of ij is equal to 1 when I is equal to j. It's equal to -1 when j is equal to I plus 1, and 0 otherwise. So once you have the Mobius function, let us take two functions, let us say g and f, both from so whenever we are going to look at the functions, it must be from f and g from the poset, right, to real numbers or like complex numbers, something like that, right? So therefore, we look at two such functions. So let's say that g of n is equal to summation I equal to 0 to n f of I, right? So this is an example that we looked at before, but now we see it in this avatar, right? The g of n is equal to summation I equal to 0 to n f of I, right? F is also a function over the integers, g is also a function over the integers. Now this is if and only if, of course, f of n is equal to by the Mobius inversion formula, right? F of n is equal to summation I less than or equal to n g of I into mu of I comma n. Now what is this, right? Mu of I comma n is precisely 1 when I equal to j, and precisely -1 when j is equal to I plus 1, and everywhere else it is 0. So therefore you will see that this is actually equal to g of n minus g of n minus 1, and this explains our earlier observation of the same thing, right? Why it should be this way. So this is also because of the Mobius inversion formula. Another example, we can look at the positive natural numbers n plus together with the order divisibility order. Okay. So again, I asked you to derive the Mobius function of this. If you have done that, right, you would have found out that mu of r comma s is equal to minus 1 whole raised to t if s by r is the product of t distinct primes, and otherwise it is 0. Okay. So assuming that you have computed this, we can now continue, right? So now let f and g be functions defined over n plus, such that let's say g of n is equal to summation over all k the divisors of let's say, so this is n, not d. Okay, divisors of n, f of k for every n in n. Okay, so g of n is sum over all the divisors f of k. Then Mobius inversion says that f of n is given by summation over all divisors of n, right? K dividing n, g of k into mu of k comma n, right? That is the definition of Mobius inversion, right? Now, suppose so if you look at mu of r comma s, mu of r comma s only depend on what is s by r, right? So I can instead make it a one variable function by saying that mu of s by r, right, over the integers is equal to mu of r comma s. So the Mobius function can be written in just one variable in this case, and therefore let me write it as mu of s by r here. So therefore I get mu of n by k. So therefore I get f of n is equal to summation k dividing n g of k into mu of n by k. And this is precisely the classical Mobius inversion formula from number theory. In fact, this is probably the reason the name Mobius inversion stuck to this technique. That is a generalization of the classical Mobius inversion. Now we look at the product theorem. So we define the product of two posets earlier, right? So consider the Cartesian product of posets P and Q. Right? So the product theorem says that the Mobius function of the product P cross Q is given by the product of the Mobius function. Okay? So Mobius function of the product mu P by Q of x y x dash y dash is equal to mu P of x x dash times mu Q of y y dash. So the proof, I am omitting the proof here. It's very easy actually, but I can give it as a homework. So prove this above, and there are several ways of proving this. Okay? So one is by showing that so to show that this is indeed the product, you just need to show that it satisfies the recurrence, right? Or another proof method is by expanding this, right? We know what is this product, right? What is this with respect to the definition? We know what is the definition of this and this, right? As summations, and then you take the product of this and compare the coefficients and show that okay, they are also the same. So there are many ways of proving this. So I am omitting the proof, but you can work on this. How many different proofs you can come. And this is very useful. Okay, so so how to use this? Well, again, I'll give you this as a homework. So we already asked you to prove that the Bernoulli pose at Bn is isomorphic to the nth power of a chain on two elements, right? So where C is the chain of two elements, Bn is isomorphic to the product of chain of two elements with itself n times. Now, because of this property, we can use now the product theorem, right? So if you know how to compute the Mobius function of this, then you can also compute the Mobius function of the Bn by the product theorem. So now first use this to find the Mobius function of Bn, right? Show that like it is indeed the one that we discussed, and then connect it with the principle of inclusion and exclusion, and derive it as a special case of Mobius inversion. So Mobius inversion is a special case of principle of inclusion and exclusion is a very specific case of Mobius inversion. So you can prove this again using this product theorem. Another homework is to prove the dual version of Mobius inversion formula. That is, suppose the P is a poset having a 1. So in the first case, we say that okay, P has a 0. And then f and g are functions defined over P, which are real valued functions. Then again, g of x is equal to summation y containing or greater than or equal to x f of y. If and only if f is expressed as summation y greater than or equal to x, mu of xy into g of y. Okay, so just note the order, and also there is a 1 here, right? It's different from 0, and then work out the details similarly. So this is called a dual version of the Mobius inversion formula. Now I want to wind up with a slightly different topic called involutions. It's a very brief introduction to involutions. We just look at a single example, and then we formally define it, and then that's it. So let us look at an example. Suppose you are asked to prove this, something which you already done, right? Prove combinatorially the summation k is equal to 0 to n choose k into minus 1 raised to k is equal to 0. Okay, for n greater than or equal to 1. Now we already have seen a couple of proofs of this, but now I want to prove this using, let's say, involution. So what is involution? I will define soon, but for the time being, let us just look at the proof. So let me denote by x the power set of the set 1 to n, right? Which is the base set of the Bernoulli poset, right? So let us look at the set x, and then you take any subset of 1 to n, and then define the sign of the set S as minus 1 raised to the cardinality of S. Okay, so the sign of the set is minus 1 whole raised to its cardinality. So this I can define for every subset of 1 to n, or every element of the power set. Now, for for any k, right, n choose k subsets S of the set 1 to n has cardinality k, right? That is by the definition of n choose k, right? That is what we call n choose k. And therefore, all of them have sign minus 1 raised to k, right? Minus 1 raised to k, because cardinality of S is k. So we have n choose k subsets with the sign minus 1 raised to k. Okay, so what I can write, the sum that we were looking at, summation over all all the elements in X, sign of S is precisely summation k is equal to 0 to n. N choose k because that many elements have sign minus 1 raised to k, right? So n choose k into minus 1 raised to k. Okay, now let us define a function I from x to x as follows. So the function I takes s, right? Thus, s is a subset of 1 to n. So I of s takes the set s to s union singleton 1 if 1 is not in s. Okay, so if the element 1 is not in the set s, then I add it. Right? So I just add it to s. On the other hand, suppose s contains 1, then I'll just remove it from s. So it is s minus singleton 1. So I takes s to s union 1 if 1 is not in s, and it will take s to s minus singleton 1 if 1 is actually in s. So we can observe that I is its own inverse, right? I of I comma s, I of s is equal to s because if phi of s is this form, then I'm going to add it back, right? In the the next step, I of s. And if it is this form, I'm going to remove it. So in whichever case, I will get I of s is equal to s. So therefore, I is its own inverse, and I square is equal to identity, right? So I into I is the identity of x. So I is a bijection because I square is identity. I is a bijection, and of course again its own inverse. Now what is the sign of I of s? Well, because s takes elements from whatever its cardinality to either its cardinality minus 1 or its cardinality plus 1. Right? I am going to either add or subtract exactly one element. So this will be minus sign of s because minus 1 raised to the cardinality is different, right? And I pairs each positive object with a negative object, right? Because that is what I does, right? So if this was of sign positive, then it's going to set with the negative sign because the cardinality, the parity of the cardinality changes. So therefore, summation sign of s is equal to 0. If you take all s in x, right, sign of s is equal to 0. So and that is precisely what we had here, right? So that is precisely this thing. So therefore, by this observation that we have shown that it is 0. So this is a proof using the idea of involution. So what is involution? Well, so an involution on a set x is a function that maps from x to itself such that its square is the identity, which means that I is a bijection and I is its own inverse. Now, if you take an involution, I call fix of I as the set of all elements that is not unchanged under I. Okay, so all the elements x in x such that I of x is equal to x itself. So this set may be empty because I can change. For example, in the previous case, we saw that this set is actually empty, right? Because we will take all the odd sets to even sets and even sets to odd sets. So therefore, there is no element that is fixed. So fix of I can be the empty set also. Now, I is a sign reversing involution with respect to a sign function sgn. Okay, let's say that sign function sgn maps x to plus 1 and minus 1. So I is sign reversing if and only if for all the elements that are not fixed by I, right? So all the elements that are not fixed by I, the sign actually changes, right? So sign of I of x is equal to sign of x minus sign of x. So of course the fixed elements will not change the sign, right? But the sign function is already fixed, right? We are not going to change the sign function. We are only looking at what happens to the elements after the the image, right? Under the image. So if sine of I of x is equal to minus sine of x for every x in x minus fix of I, right? Those elements that are not fixed by I. Then I say I is a sign reversing involution. And then we have the involution theorem. Right? So what is the involution theorem? That let us say that x be a set which is signed with a function sgn, and I be a sign reversing involution on x with respect to the function sgn. Then summation x in x sine of x is actually equal to summation over all the elements fixed by I sine of x. Okay, so this is the involution theorem, okay? And this is quite useful. You will see in your homeworks, and the proof is almost trivial, right? So just looking at it, we can see that why this should be the case, right? Because if you look at all the elements that are not fixed by I, right? So I basically takes the element that are not fixed and changes the sign, and because the square, right, I applied again, will get back, right, in that it's a bijection, right? So we can see that the number of elements that has the plus sign must be equal to the number of elements that has the minus sign, right? And therefore they will cancel out, and those are the guys which are outside the fix of I. So therefore everything else will be added to 0, and therefore the remaining things will be those elements in fix of I with its own sign. So that is the idea, right? So that's an informal proof. Now if you want to formally prove this, we can also do that, right? So just by defining these things, right? So let's say that x plus is the set of all elements in not fixed by I whose sign is plus 1. X minus is those elements not fixed by I whose sign is minus 1. Then the involution I restricted to it's a function which is restricted to the set on x plus is something which takes x plus to x minus, right? And then the involution restricted to x minus takes x minus to x plus. Now we know that I is an involution, therefore it's a bijection. So therefore ix plus must be ix minus inverse, and similarly vice versa. And therefore because this is a bijection, we know that x plus, right, the function going from ix plus to ix minus, x plus to x minus is a bijection. Their cardinalities must be the same, and therefore the summation over all x belongs to x, sine of x is equal to if you want, of course, you can write summation over all x in x plus, summation over x in x minus, again the summation, and this will be cardinality of x plus and cardinality of x minus, and they are opposite signs, so they cancel out, and what remains is over all the fixed elements the sign of x, and that is the formal proof. Okay, so here is a couple of homeworks. Using involutions, prove that this identity, binomial identity, summation k equal to 0 to n minus 1 raised to k 2n choose k is equal to minus 1 whole raised to n 2n minus 1 choose n. Again, you can think of proofs using involutions, you can think of proofs without using involutions, combinatorial proof again, and you can also look at algebraic proofs. So you have 3 different ways of proofs you can think of. But in this homework you should do this. Then as we mentioned, no, I did not mention this, maybe, right? You can also prove inclusion exclusion formula using involution. Okay, so give a proof of inclusion exclusion formula using involution. I think with that we stop for today, and see you next week.